Hello everyone. Welcome to part 8 in our series on the derivative. Today we're going to be looking at an application of derivatives. Namely, we're going to be using the first derivative to help us graph the function. Okay. First we need to talk about a couple vocabulary words. You may know these words already, increasing and decreasing. But in math they have very specific meanings, so we need to talk about that. Okay. Let's say I have a function and it's defined from, let's say 0 to 10 or something like that. If for any two numbers a and b such that a is less than b, if f of a is less than f of b, then we say we have an increasing function. There's my function. And that has to be true for any a and b in that interval, where a is less than b. In that case, we say f is increasing. Similarly, if I have a less than b again on some interval, and this time f of a is bigger than f of b, well, that's what we call a decreasing function. Let's see if I can draw that this time. Okay. So that's the picture of an increasing function and a decreasing function on some interval of x. In this case, I've drawn it from, let's say, 0 to 10. Now, how does this relate to the derivative? Well, the tangent line to this curve is going to have a positive slope. The tangent line to this curve is going to have a negative slope. So this is how we connect the derivative to these two cases. Here, f prime of x is positive for an increasing function. Over here, f prime of x is negative for a decreasing function. So before we even see the graph, if I have a curve whose derivative is negative on some interval, we know that it's decreasing on the interval. If I have a curve whose derivative is positive on some interval, we know that the function is increasing on that interval. Okay, let's use that information to help us graph a curve. Here we go. F of x is x cubed minus 3x. Well, if we're going to use the first derivative to help us graph, first thing we have to do is find the first derivative. Okay, f prime of x equals 3x squared minus 3. Okay, I'm going to factor that, take out a 3. Oh, and I can factor that again. Sorry, let's take out that 3. 3, difference of two squares, x plus 1, x minus 1. Okay, that's about as far as I can go. Okay, why did I do that? Well, what we're going to try to do here is set up a nice table for ourselves. It's going to take two columns, and you don't completely have to do this. This is just one of these things that helps us organize our information. This is going to be the derivative of f on the right-hand column, and in the left-hand column, we're going to put intervals of x. Okay, how do we fill this table in? So I look at my derivative, and I say, when is this derivative equal to 0? And this is why I factored. It makes it really easy. What values of x make this 0? Well, x equals minus 1. That would make this part 0. And x equals positive 1. That would make this part 0. So these are the only two x values which make my derivative 0. Why am I worried about 0? Right? We just spent some time talking about positive derivative and negative derivative. Well, what's neither positive nor negative? It's 0. These x values are going to be the dividing line between the intervals that have positive derivatives and negative derivatives. So the first thing I do is I put these values in two rows of my table, put them in there with spaces. Okay, so here we go. X is minus 1 and x is 1. Now, why do I put spaces? Well, put all the intervals that go either to the left or to the right or in between. What do I mean by that? Okay, what's to the left of x is equal to minus 1? Well, less than minus 1. What's in between these two things? Well, that's x is greater than minus 1 and less than 1. And what's past or to the right of x equals 1? Well, that's x greater than 1. There we go. Now we can fill in my right-hand column. Well, we already know that x equals minus 1 is a zero derivative. X equals 1 is also a zero derivative. And in this column, I'm not worried about the actual values of the derivative. I just need to know, is it positive or is it negative? And how do you do that? Just plug in easy values of x. Or just make up numbers so that it's obvious what the sign of f prime is. So for example, what's any number which is less than minus 1? Well, I don't know, how about minus 10? If I plug in minus 10 into this term, I get a negative number. If I plug it into this term, I get another negative number. You multiply two negative numbers, you get a positive number. So the derivative for this row is going to be positive. That's an increasing part of the function. On the interval x less than minus 1, the derivative is positive, so the function's increasing. How about this interval? What's an easy number to plug in? I would say 0. 0 plugged into this gives us a positive number. 0 plugged into this gives us a negative number. The product is negative, so the function is decreasing. Finally, if x is greater than 1, let's plug in 10. This is positive. This is positive. The product is positive, so the function must be increasing. Notice how I really never bothered to figure out what the actual value of f prime is, just whether it's plus, minus, and of course whether it's 0 or not, which I already did. Now it's useful for the zero derivatives to plot some points, right? So when x is minus 1, what point is this on the curve? Make sure you plug into the original function. Don't plug into the derivative. That's just going to give you 0 again. So if I plug in minus 1 to this, I get minus 1 plus 3. That is 2. So minus 1 and 2. That's a point on our curve. I'm going to go over to my graph and put that point right there. Okay, how about this point? Well, if I plug in 1 here, I get 1 minus 3. That's minus 2. Let's use a different color. So that's 1 and minus 2. If I go over to my graph, that looks like this. Okay. Let's just plot a few more points. That can often help for the numbers in between. And I always just plug in easy things, right? So if I plug in x equals 0, I get 0. So that goes right through here. If I plug in minus 2, let's see, minus 8 plus 6, that's also minus 2. Okay, so minus 2, that's about here. If I plug in 2, I get 8 minus 6, that's 2. So the curve goes through the point 2, 2, that's here. And this is basically all I'm going to do. I'm not going to go any further. Again, use the derivative to help you. The function is increasing here, right? So what's the increasing function look like? It must look like this. It goes up to here, right? It decreases according to our table, goes through here. And then once I get to this other blue dot, it increases again. So can you visualize what this curve looks like? I'm going to draw it in right now. Okay, I'm not going for super precision here, but let's see if I can do okay. Yeah, not too bad, right? There it is. That's our curve. We got that by just plugging in for minimal points. I actually only plugged in for this, what is that, 5 points? That's not bad. The derivative really told us a lot about what's going on in between these 5 points. Okay, let's talk about this graph again without all the numbers getting in the way. Right, we found that we had this orange dot, The derivative was 0 there, right? Can you visualize what the tangent line looks like there? It's going to look like, let's see if I can draw it in, something like this, right? It's horizontal. That's why we have a slope of 0. How about down here at this blue dot? Also, derivative of 0. Okay, that was pretty bad. Let's try again. That's a little better. Okay, there's another horizontal tangent line. So in both these cases, the derivative was 0, but you can see that on the curve, things are kind of different. Right? This one is a peak. This one is a valley. How do I distinguish between those two things just looking at the table, just looking at my derivative table, not looking at this curve? Because there is a difference here. What we're going to do is use what's called the first derivative test to distinguish between these 2 points. Okay. Here's our 4 possibilities. And here's our orange dot again. There's our blue dot again. Okay, this orange dot is what we call a relative maximum. Sometimes we also call it a local maximum. Why do we call it that? Well, the dot is higher, and by higher I mean at a greater y value than any of the other points on the curve that are close to it. Right? That's a key point. Any point close to it, that's what we call it a local maximum. Okay, so I'm going to write that down, put it in orange. Local maximum. And again, if you hear the word local, you can also substitute relative. That's the same thing. This blue dot here is what we call a local minimum. The y value of the blue dot is less than the y values on the curve that's close or nearby to the blue dot. Now, it isn't to say that this is the lowest y value or the least y value that the function attains. As we saw back here, let's go back. The function, after bottoming out here, yeah, that's the lowest y value close to the blue dot, but you notice way over here, the y values are actually less than the blue dot. Similarly, with our local or relative maximum, yes, the orange dot is greater in y than all the other points on the curve close to it, but if you go far enough away, the curve has now surpassed the orange dot in terms of y values. So that's why we call these relative or local maximum and a relative or local minimum. Okay, back to our cases. Okay, now in this case, we did have f prime equals 0, and in this case, we did have f prime equals 0. How do I distinguish these two? What you do is that you look at the derivative on the left and the right. Here we have a positive derivative, here we have a negative derivative, right? And we can get this from our table. On the left of this orange dot, if we have a positive, and then that shifts or changes to a negative derivative on the right-hand side, then this dot, this point, must have been a maximum, a local maximum. It just flips for minimums. Negative on the left, positive on the right. And again, I'm talking about slope, right? The slope of this curve is negative here. It's positive here. If we go from negative to positive, then this dot must be a minimum. Okay, so those are the 2 cases that give us either a local maximum or a local minimum. Now there are 2 other cases where we don't get that. Here we have a negative slope followed by another negative slope. On the right-hand side here, we have a positive slope followed by another positive slope. These dots are neither minimums nor maximums. And there's actually no word for them. I think of them as ledge points. If I imagine walking up this mountain and this function tells us what the elevation is, well, here we level off, but it doesn't go back down again. It continues up. So this is not a maximum and it's not a minimum. It's neither. But it was true that the derivative was equal to 0 in both of these cases. It does actually flatten off. You do get a horizontal tangent line there. Which goes to show you, right, if you find the derivative is equal to 0, it doesn't mean that there must be a maximum or a minimum, because it could be these 2 situations as well. Okay, let's do one more example. Okay, let's try to graph this function. What's the first thing that we do? Yes, you're on top of it. Good job. We take the derivative. F prime of x is 4x cubed minus 12x squared. As always, I factor. What's the most I can take out? What's the greatest common factor? It is 4x squared. And that's going to give me x minus 3. That actually factored really nicely. It's pretty easy to see what values of x make this 0. X equals 0 is 1. X equals 3 is the other. Okay, that's really not that bad at all. Okay, let's make our table. I have a little more room this time, it feels. Okay, this is our f prime. I use the values that made the derivative 0 to tell me how to fill in the table, so I put these in first. Make sure you put some space for yourself. So x equals 0 goes here, x equals 3 goes here. The other rows are just the intervals of x that surround those points. That's it. Hopefully you got that yourself. What else do we know? We know that the derivative is 0 at these 2 points. And to get what's going on here, just plug in easy numbers. Now, I notice that if I come up here, I'm not going to bother to plug into this, into the x squared term, because that's always positive. That's not going to change our result. So let's just plug it into this. If I plug in a big negative number, by big I mean like minus 10 into here, well, that's negative. The function's decreasing when x is less than 0. If I plug in a number between 0 and 3, well, that's still negative. Okay, so the function's still decreasing. Only one more to do. If I plug in a number bigger than 3, let's say 10, this is positive. Okay, the function is finally increasing now. It's been decreasing all this time up until that point. Okay, so first let's figure out the point, right? When x is 0, remember to plug into the original to get the y value of the point. That's going to give me 12. Okay, how about this other one? When x is 3, if I plug in 3, okay, it's a little nasty, but 81 minus 4 times 27, so that's 81 minus 108, if I did that right. Okay, minus 27 plus 12, I think I got minus 15. Hopefully that's what you got too. Okay, now can we look at our table to see what these are? Well, you notice that surrounding this row, I have a minus and a minus. The function's decreasing on both sides. So this is what I called that a ledge, didn't I? It's not really an official word, but that's what I call it. How about this one, though? I have decreasing function on the left, increasing function on the right. If you just visualize that, this is a local minimum. Okay. Okay, let's plot some points. So I know it goes through 0, 12. That's right here. I know it goes through 3 minus 15. Okay, that's way down here. But that is our minimum, so hopefully it's not going to go lower than that. I might want to try to plug in a few more points just to see roughly where we are. Okay, so if I plug in, let's try how about 1 and 2. If I plug in 1, I get 9, it looks like, right? 1 minus 4 is minus 3, plus 12 is 9. So I'll put that point here. Okay, how about plugging in 2? I get 16 minus 4 times 8. Let's see, that's minus 32. So minus 16 plus 12. So it looks like we're at minus 4 when I plug in 2. So, okay, that's something like here. Okay, I think I have an idea of what's going on. If I plug in 4 into this thing, 4 to the 4th, well, that's a pretty big number. Actually, it's going to give me 0 here if I plug in 4, isn't it? These two things. So I'm actually going to get 12. So I can actually do that one too. I didn't think I was going to be able to do that. That guy's over here. So we know this is going to cross between 3 and 4 and between 1 and 2. Then the rest of it, we use a table. We know it's decreasing, the function's decreasing for negative x. Okay, so that means that the thing looks like this. All right. This is a ledge, right? It's neither a minimum or a maximum because it continues to decrease until it gets down to here. And then finally it starts increasing. It goes through our point there. I know there's a little few squiggles there, but that's okay. That's what you get when you draw a graph by hand. But that's the graph. And that was a pretty complicated looking graph. But we only had to plot 1, 2, 3, 4, 5 points, and coupled with our first derivative test table, we were able to figure out what the graph looked like. Well, that's it for this video. I hope you enjoyed it, and I'll see you next time.